Hello again. I'd like to go over those three graphs of motion, xt, vt, and at, for three situations that summarize many kinds of motion we observe. If you were going to watch this short video and take some notes, in a perfect world, you'd have a piece of paper that had three xt graphs on it, three VT graphs on it, and three acceleration time graphs on it. But if you are careful and you have colored pencils and you use a different color for these three situations, one for at rest, one for constant velocity, one for constant acceleration, you could probably get by with just three graphs and color code those situations. And that's the way I'm going to do it here. So again, what I'd like to get at is what does it look like on a distance time graph for an object that's undergoing those three types of motion. What does it look like on a VT graph for an object experiencing successively those three types of motion, being at rest, moving at a constant speed, moving with constant acceleration. Okay, so I am going to use purple for being at rest. If you are at rest, then you are not changing your position as time goes by. You are in the same place during time 0 that you are during time 1 second, or 2 seconds, or even 3 seconds later. You have not been displaced. Now that line could be at 0, but you also could be at a place called 2 meters or any other place. But that line has 0 slope. It's horizontal completely because this is where you are as time goes by, and you are not changing where you are. Time is going by, you are not changing where you are. Now when you're at rest, your velocity is 0, right? Because you are not moving. So our VT graph has to be a 0 slope line, but at a value of 0 velocity. And I hope this is also intuitive. If you're not moving, then you're not accelerating. Because acceleration is change in velocity, and your velocity is 0 the whole time. So this also has to be a horizontal line at a value of 0 meters per second squared of acceleration. For moving at a constant velocity, let's use red. Now, if you're traveling at a constant velocity, the thing that equals 0, of course, is what? If you're not changing your velocity, the thing that equals 0 is your acceleration. And I could do that right now if I wanted to, but let's just do it in the same order we did it before. So when you're moving at a constant velocity, and again, I could start at 0. I don't have to start at 0. I could start at any old place. Say you started at a place called 1 meter, and that's 1 meter right here. But if you're traveling at a constant velocity, your displacement is going to be linear. I'm starting to regret not using a straight edge or a meter stick for that, but I think you'll excuse me this time. Again, it could go through the origin, but it doesn't have to. Constant velocity means your velocity is always the same, like cruise control on a car. You're going 65 miles an hour down the freeway to LA on Highway 5. You're probably going faster than that, but the point is you set the cruise control on, and so your velocity is not changing. always the same value, whatever this value is your velocity. I alluded to this a minute ago. If you're not changing your velocity, your rate of acceleration is 0. And that means, again, we have a line at 0 meters per second squared of acceleration for a constant velocity situation. Lastly, we'll use blue for constant acceleration. Now, that means you're changing your velocity, but at the same constant rate every second. In the prior video, it was 10. On Earth, negative 9.8, 10, whatever. So but your value of acceleration is not 0, it's 10 or 9.8 or whatever. Now, technically, it should be down here in the 4th quadrant, but if we just allow me to pretend like it's positive 10, or I treat the downward direction as positive today, that's what constant acceleration is. And a lot of kids say, well, that nothing's happening. That's a straight line. Yeah, nothing's happening on the acceleration time graph, but a lot of things are happening on the other two graphs because you're changing your velocity by this rate. Let's say this is 10. So that means every second you're going 10 meters per second faster than you were the second before. What does that look like on the VT graph? We just talked about that a little while ago in a prior video, but assuming you start at 0, you have a linear increase in velocity. And again, we saw that leads to distance changing with the square of time. 1/2 at squared is our displacement equation for constant acceleration. That causes the distance to be ever greater in later seconds than it was in earliest seconds. Now, the last thing I really want to talk about is slope. You know, in math class, you calculate slope, it's a number. 3/2, negative 1/5. Slope could be 2. But it's just a number. But in physics, the slope has a quantity. Now, a minute ago, I used different colors for different situations. And I'm just going to draw it with black pen, a linear relationship for the first two graphs, okay? Now, these are clearly not the same thing because this is constant velocity and this is acceleration happening. So don't be confused with respect to that. I just want to talk about slope a little bit. The slope of any x versus t graph is always velocity. Why? Well, slope is the rise, the change in the y-axis thing, divided by the change in the x-axis thing. And on this graph, the y-axis thing is distance in meters, and the x-axis thing is time, change in time. In fact, let's not even put that delta there, which is measured time, is measured in seconds. So the slope has units of meters per second. So if you had real values here and you could calculate the numerical value of that slope, it would be the speed or the velocity of that object. So here, slope is velocity on an xt graph. On a vt graph, slope is the same, rise over run, but now the thing on the y-axis is the velocity. So we have the change in velocity is going to be, like if you pick 2 points on this line and you calculate the slope, this would be final, this would be one velocity, this is the initial one, so that you subtract them, you get the change in velocity. And the run is the time. Again, going to units because they're so helpful, velocity is measured in meters per second, and the time is measured in seconds. And meters per second is meters per second squared, the unit of acceleration. So the slope of this graph, of any VT graph, the slope is always the acceleration. If the slope is constant, then it's constant acceleration. If the slope is 0, then it's 0 acceleration. The slope is the acceleration, and that's helpful to keep in mind when analyzing graphs of motion. What's the slope of an acceleration time graph? Well, it turns out that it's the rate of change of acceleration, which has got a funny name. It's called the jerk. I'm not going to ask you to remember that, probably. But here the slope is the change in the acceleration, which is the change in meters per second squared, divided by the change in time, which is seconds. And that's meters per second cubed, which is actually a quantity called the jerk. That's probably all I really want to say about that. The last thing I'd like to really quickly look at is area. You might remember we did a buggy lab, a virtual lab, and I was all excited about asking you about what the area under the xt graph meant, and we came to find out that it was meaningless. Let's say this is 3 seconds, and this is 10 meters per second squared. And in math class, area, again, is just a number. It's something you calculate. We don't think often about the units. I mean, they're always like feet squared or meters squared because area is a square thing, two-dimensional thing. But let's look at it. The area under this curve is this area here that I've cross-hatched in red. But look at, and we know area of a rectangle is base times height. But let's look at what's going on. The base, it has a unit. It's 3 long, but it's seconds is what it's being measured in. And the height is a rate of acceleration. In this case, I said 10 meters per second squared. Well, looky there. The second here cancels the square here, and our area turns out to be 30 meters per second. The area under that curve is the rate of change of velocity. It's actually the change in velocity. If you start at 0, then it is the final velocity. But if you started at 10 and you added 30, you'd be going 40. But it's the change in velocity. What about the area under any? That's true of the area under any AT graph. It's always the change in velocity. What about under a VT graph? Well, again, let's just make up a number so we can play that game. Let's say this is 4 seconds, and that this velocity here is, I don't know, 6 meters per second. Let's calculate the area under the curve, so to speak. I know it's not curved, it's a line, but we call it a curve. Any plot is a curve, technically. Area of a triangle is 1/2 base times height. But again, they're not just numbers. The base is 4 seconds. And the height is 6 meters per second. It's not just 6, it has a unit. And again, this second on the top, so to speak, cancels the second on the bottom of this term, and 4 times 6 is 24, half of that is 12, and the unit is meters. So the area under a velocity time graph is the displacement. This one, you may recall, is the one that is meaningless. Really fast. Let's say that's 2 seconds. Let's say that's 5 meters. Area of a triangle is 1/2 base times height. The base is 2 seconds, I said. The height is 5 meters. But again, some attention to the units tells you that this is a meaningless quantity. 2 times 5 is 10, half of that is 5, but the point is the area has units of meters times seconds or meter seconds, and in physics, or for that matter in the world, that's a meaningless quantity. Like, it doesn't mean anything. Whereas here the area is how far you moved from where you started, and here the area is how much did your velocity change by. Slopes and areas are important, and they help you calculate things sometimes, but in the case of the slopes, they just help you remember what's happening. I'm going to ask you a few questions at the end of this video, but let me just prime the pump and ask you one right now. You have an xt graph, where you are as a function of time going by. And that graph looks like that. So what's that object doing? One way to analyze this is to think about slope. The slope of any xt graph is meters over seconds or meters per second. The slope is the velocity. No matter what the shape of the graph, the slope is the velocity. Meters on the y-axis divided by time, seconds on the x-axis. Slope has units of meters per second. What is the slope doing? Is it 0? No, the slope is not 0. That would be a 0 slope. Is the slope constant? No, that would be a constant slope, or that would be a constant slope, but it's not staying constant. It is increasing. And if the slope is increasing and the slope is the velocity, then this is a situation where the velocity is increasing. And that's true because this is the graph we get from acceleration, constant acceleration. Answer the rest of the few questions I present, and I'll see you in class.